This video is on angle of fire corrections. Like I said on the last video, this one's a little more straightforward than perhaps some of the other ones have been. Relatively simple process in getting this stuff figured out. So let's first start, let's just dive right into it and start with some definitions here. For angled shots, like if you're operating in a mountainous or hilly terrain where your target's going to be at a different elevation than you are, you're going to have to consider two different ranges. The first range is, here's a picture of we have a shooter at an elevated position up on a hill, and down in a valley we have a target. So there are two different elevations. And when you're at your firing position, what you're going to do is you're going to range your target, and you're going to get what is called a true range, which is the actual straight line physical distance between you and your target. The other range we need to consider is the actual horizontal range. And that is the horizontal distance between you and your target, not counting the vertical distance. So, for example, if we look at this, we have a triangle, a right triangle, and the top line there, the actual horizontal range, that's one leg of the triangle. And then if you look at the true range, that would be the hypotenuse. Now, these two different legs, the hypotenuse and this leg on top, are going to be different lengths, obviously. And if you just consider the shape of a triangle, if you look at the true range, the hypotenuse, the blue line on the bottom there, that's going to be a longer line or a longer range than the top one is. So your true range on angled shots is always going to be longer than your actual horizontal range. So that's the first thing to consider. And the more steep of a shot it's going to be, the shorter your true range is going to be compared to your actual horizontal range. So that ratio is going to change depending on your angle of fire. Now, why this is all important is because I don't know if you've ever shot at long distances up or down major slopes, but one thing that happens when you're shooting either upslope or downslope, doesn't matter which way, but when you decrease your actual horizontal range, your point of impact is higher than it would have been if you would have had the longer actual horizontal range if you're shooting just straight across horizontally. So basically, if your rifle is zeroed at a given range, say 1,000 meters or whatever, and that you're perfectly zeroed for that at an actual horizontal range, you're just shooting on flat country. And then you're operating in slope terrain and you see a target standing way lower or higher than you. You're either downhill or uphill. When you shoot at it, you're going to hit high. Now, a lot of guys think that there's an inverse relationship here in that when you hit high while shooting downhill, intuitively, you would think that if you're shooting uphill, you must hit low. But actually, that's not how it works. You'll find that either uphill or downhill, if you're shooting 15 degrees downslope, you're going to hit just the same amount of distance high as you would if you're shooting 15 degrees upslope. It's still going to hit that same amount high. The reason for that is the actual horizontal range was decreased. That's the range that the gravity is going to have the effect over, okay? So when you're considering the drop of our bullet due to the effects of gravity, we're going to use our actual horizontal range to determine our bullet drop due to the force of gravity. Now, the true range is still important. The true range is the actual amount of distance that the bullet has to travel to make it to the target. So you have to cut through all that atmosphere. Now, even though the effects of gravity is only going to be affecting your bullet for the actual horizontal range, the drag effects due to the atmosphere on your bullet are going to be dependent on the true range. That's the actual physical distance between you and the target. And remember, if we look at this triangle again, that's the hypotenuse. That's the longer one. So it gets a little confusing here. So you're going to be adjusting your bullet drop for the effects of gravity according to your actual horizontal range, which is going to be shorter than your true range. But all your atmospheric effects, such as wind, changes due to barometric pressure or ambient air temperature, those effects you're going to want to correct according to your true range. So a real common misconception in long-range shooting is that you simply calculate your actual horizontal range by using cosine or whatever you're using, and simply look up all your ballistic data for that horizontal range. And like we said before, what you're going to do is you're going to have basically not enough of the atmospheric effects compensated for in that formula, because like we just said, the true range is a longer distance than the actual horizontal range, and you have to account for all that extra atmosphere in there. So we have to separate those two things. So both ranges are actually important. Now, a lot of rangefinders, laser rangefinders that you'll find nowadays that are made for long-range shooters actually have inclinometers in them, which determine the angle of the shot, and they'll have the computer on the inside of your rangefinder actually figure out your actual horizontal range for you. And so you want to make sure that when you're reading your laser rangefinders, that in your display you have both the true range, which is the actual measured distance to the target, and the actual horizontal range, if it does have that feature. Now, if all you have is the true range in your rangefinder, that's going to work just fine as well, because it's actually quite simple to be able to calculate your actual horizontal range. And in our peripheral equipment selection, I did indicate that you're going to need a scientific calculator, and that is an important tool to have. Another thing you're going to need is some kind of way to determine your angle of fire. Now, I would strongly recommend using the Mil-Dot Master, because that's just such a slick piece of equipment that you can, it works for a lot of different purposes, and it does have kind of a protractor built into it, so you can do your angle of fire calculations just with your Mil-Dot Master. You hang a weight on a string from the corner of this deal, and you pinch it off on the side. It has a readout of your different angles. And then it'll also, it's an analog calculator. If you flip it over the other side, it'll give you actual horizontal range corrections for the different degrees of slope. So that's a pretty slick tool. If you don't have access to a Mil-Dot Master, another way to do this is to get a protractor. It's like one that you find at the store. And you can get some super glue and a heavy-duty plastic straw or whatever, some kind of tube to look through. And you'll kind of glue that onto your protractor. You want to make sure it's centered right on that 90 degrees or that 0 degrees mark there. So you glue that straw on there, and that's what you look through. And then you'll attach a string where kind of the vertex of the angle is there, and you'll tie a weight onto the end of that string, and what you simply do is you just kind of look through that straw, upslope or downslope to whatever your wherever your target is, and then you let that string hang there with the weight, and then you just kind of pinch it and look at it. And that'll give you your degrees of your angle of fire. And then we simply take the cosine of that angle, multiply it by our true range, which we've determined either using a laser or by using the Mil-Dots in our scope, and we'll discuss that later. And so that'll give you the actual horizontal range. So let's do an example here, a couple of them, so you can kind of get an idea how simple this is to calculate your actual horizontal range from your true range. And then we'll take a look and see what kind of effects that has on trajectory, and then some of the other complications that do occur when we're talking about angle of fire shots due to the difference of the relationships of the true range kind of being the basis for all your atmospheric calculations, and then the actual horizontal range being the basis for your gravitational bullet drop part of the calculations. So we'll have to figure out how to make all this stuff fit together and give us the right answer here. So let's consider this picture here. Let's do a relatively low angle shot first. And we're going to have an elevated position over your target. So the FFP is on your left there, that red box. And we're going to, first of all, get our true range. We're going to get out a laser rangefinder or use trigonometry using the Mil-Dots in our scope to calculate the range. And let's say that we find out that our true range, the actual distance from us to the target, shooting straight at it, is 1,000 meters, just for the sake of keeping this simple for this example. So our true range is 1,000 meters, okay? How do we find out what our actual horizontal range is? Because if you look at this here and you draw a straight line going up from the target, that actual horizontal distance is shorter than the true range. Well, in trigonometry, if you know the angle and the distance of the hypotenuse, you can calculate the distance of that top leg, that actual horizontal range part of the triangle. And this is quite easy. All you do is use cosine. So you get out your scientific calculator, and you can also make charts too and keep those in the field, but it's probably good to get used to typing this in so you understand how it works. A lot of times when you just rely on your charts all the time, your brain starts to get kind of rusty, and then when you lose your chart or can't find it quick enough or whatever, or if something really goofy starts happening, you don't understand the concepts, and it'll really throw you off. So it's good to actually walk through the steps of the process here. I'd recommend using your calculator in the field to figure out your actual horizontal range. So to figure this out, first we need to determine our angle to the target, and you can either use your mil.master, your angle cosine indicator if you're one of those fancy guys who has that cool little gadget you can put on your scope. You can use the protractor or whatever, or your laser rangefinder might give you that option just to read that out for you. So we'll say our angle is 15 degrees. So we simply take our calculator, we hit the cosine button on the calculator, followed by the number 15. And then if it's, depending on what calculator it is, you might have to close up the parentheses or maybe not, but you just basically hit equals after that, and that'll give you a cosine. And if your calculator's giving you crazy numbers that ain't matching up with mine, you might be in the units of radians. You're going to have to read the instructions on your calculator, go through there, and switch it over to degrees for this purpose, okay? There's two different angular systems of measurement that your calculator is going to be familiar with, radians or degrees. So for figuring this out, if we're using degrees as our system of angular measurement here, you're going to want to have your calculator in degrees, obviously. So basically type in cosine, the number of degrees, 15, hit equals. That should give you a cosine of about 0.965925826 or something like that, okay? Then you simply take that number, and that's basically the percentage of the true range that's going to equal your actual horizontal range. So you take that cosine number, which was 0.96, or 96% of 1,000 meters. So you just multiply it out, and there you go. Your actual horizontal range is 965.9 meters, something like that, okay? So it's going to be 96% of whatever it was. Now, if your true range changes, obviously, it's going to have the same relationship, but it's going to be a different number each time. So what you would do with this information is, okay, you'd look at your drop tables, and instead of using your bullet drop for 1,000 meters, you're only going to use the bullet drop information for the 965 meters. So you go to your ballistic tables, you find where you have your data for 965 meters, or you interpolate based on whatever kind of table you're going to use, and you figure out what that drop would be for that exact range, and that's what you index on your optic. Then what you do is you go and make all your corrections for wind using the true range, not the actual horizontal range, but the actual distance from you to the target. That's how much air is between you. So then you go to that same ballistic table setup that you're using, and you look at the information for wind for 1,000 meters, not 965, but 1,000 meters. And that's the windage you're going to dial in. Likewise, with your corrections for ambient air temperature, humidity, or barometric pressure. Any of your atmosphere, anything that's going to change your atmospheric density, the amount of drag on your bullet, that you're going to calculate using your true range. So that's something that you got to get sorted out. Let's take another look at an example. Here's a situation where we're taking a much steeper shot. In this case, the FFP is really elevated, and you're shooting really, really steep down this cliff at about a 40-degree angle, okay? And that's, if you're operating rugged terrain, that's not unheard of. That does happen sometimes where you're shooting at a steep angle like that. So let's just practice this out again and do it again. First thing we do is we determine our true range. Again, just for the sake of keeping it simple, let's say that we're still shooting. Your true range here from the firing position to the target is 1,000 meters again. Now, if you look at the shape of this triangle, we're a lot steeper. So your hypotenuse is actually going to be a lot longer in relationship to your actual horizontal range. Your actual horizontal distance is going to be less than it was last time because just the shape of the triangle if you look at it. So let's type in, all right, we got a 40-degree triangle. So hit the cosine button. and then 40 and hit equals. Okay, the cosine for the 40 degrees is 0.766, or about 76.6% of the true range. So that would work out to be your actual horizontal range. In this case, if your true range is 1,000 meters, you just simply take that times your cosine, which would be about 766 meters actual horizontal range. So if you didn't correct for that, you would have had problems. And let's see what that would have looked like. So this is a 40-degree angle. The difference between your actual horizontal range and your true range, each different line, your actual horizontal range is only 766 meters. Your true range is 1,000 meters. That's like a 234 meter difference. So that translates to quite a bit of difference. That's a 3.9 mils. If you're talking, we're just using my 338 Lapua Magnum this time for an example, in my 300 grain Match Kings. This is just based off my charts, but that's going to give a difference of 3.9 mils. So I would have missed 13 feet over the top of this target standing at 1,000 meters of true range if I wouldn't have corrected that for actual horizontal range. So I would have hit high, like almost 4 mils, or about 13 feet at this range, okay? So that's a huge amount. You do have to correct for angle of fire. Now, the steeper it is, the more you're going to miss by, and the longer the ranges are, the longer you're going to miss by as well. So when you're closer, this effect is reduced, and when your angles are not as steep, then it's not as important. And let's take a look again at the example we just looked at before, where we only had the 15-degree slope. Now, you'll find once you get some experience shooting up slope and down slope, that 15 degrees is a very, very small amount of slope. That's a very, very skinny triangle out there in actuality. So on our 15-degree slope shot that we showed you before, our difference between the actual horizontal range and the true range was only 35 meters of difference. Now, that's enough to translate into a miss of about a foot for 1,000 meters with the 338 loads that I'm talking about. So both these examples, your true range was the same, 1,000 meters, and your actual horizontal range was quite different just because of the angle difference. Now, if you would take the firing position and the target and swap them, and you were shooting from the bottom of the hill going up, you'd have pretty much the same effect on the gravity of the bullet, because the actual horizontal range is the factor. It doesn't care whether you're shooting up or downhill. It's the actual horizontal range that is changing how much grip gravity has on your trajectory here. So if you're shooting uphill, the same thing would be true. If you didn't correct for your actual horizontal range difference, you're still covering less ground, even shooting uphill. Just because it's up, it seems like it would be harder to walk up there. But the bullet flying through the air with that explosive behind it, really, there is a tiny bit of a difference if you actually figure it out in full detail, but that's such a complicated calculation that we're not going to torture you for that. And even for extreme range shooting, 2,000, even 2,700 meters, this system is very, very, very close. So uphill and downhill shots are going to work exactly the same way. You just take the cosine of the angle and you multiply that by the true range to get your actual horizontal range. So in the case of shooting uphill, you'd still simply adjust for the 76% of the true range, which should be 766 meters of that 1,000. So you'd have the exact same firing solution going up as you would coming down, which seems counterintuitive again. And there are, like I said, there are some complications. And if you really wanted to get it down to the millimeter, you'd have to do a heck of a lot more math. But this is very, very, very effective way of doing it, even for long-range field artillery purposes. So let's consider what it would look like if we would simply ignore our true range and using that to correct for our atmospheric conditions, okay? Let's say we just used our actual horizontal range to do all our calculations, our gravitational part of the bullet drop, and all the meteorological corrections that we'd apply to that as well. And we did not consider the fact that the true range was the amount of distance that the bullet was actually covering plus the shape of the the parabolic trajectory, obviously. And let's see how much that would change us. Well, it would be less of a change at the 15-degree slope. Like I said before, the less the slope, the less all this stuff is going to affect you. But at the 15-degree slope, your actual horizontal range is for a 1,000-meter shot is 966 meters. So it's almost the full 1,000. It's like 96% of it. And let's say that your atmospheric corrections, you had to make some corrections for it's a real hot day. It's like 90 degrees, and it's 30 degrees warmer than what you're all zeroed in for your so-called standard conditions. So your thinner air is going to cause your point of impact to be higher. And the amount of air over which you're correcting is a lot longer, though, because your true range is going to be like 35 meters longer than your actual horizontal range. So how much would you have missed by for this 30-degree difference in temperature if you would not have considered your true range instead of your actual horizontal range? And you would have missed by about 8 inches. Not a whole lot, but if you're shooting at a real small target, or if you have other things that are throwing you off vertically as well, this is going to add to it. So that's a significant miss. That's enough to notice. So that's about 0.2 of a mil. So if you would have just used your actual horizontal range here, you would have missed by 8 inches over the top. Let's take a look at the steeper slope shot, okay? Again, our true range, like we said before, was 1,000 meters, but we're shooting at 40 degrees, so our actual horizontal distance is actually only 766 meters. Now, if we didn't use our true range for our corrections here, there's even a bigger difference. That's the only there's a 76% similarity between the two in this case, so there's a bigger difference. What did we say it was? Like 234 meter difference. There's 234 meters of air more on our true range than there is on our actual horizontal range here. So if you don't correct for the true range, you're going to miss out on a 234 meters worth of air resistance, and that's going to throw you off by 16 inches over the top if it's 90 degrees Fahrenheit and 30 degrees over your standard conditions. If you're shooting 30 degrees colder, it'll be about 8 inches in that case. So hopefully what we've illustrated here is the importance of both ranges. And those are both factors that you're going to use to calculate your firing solution for long-range shots. You're going to need to know both your true range. You're not going to just throw that in the garbage once you figure out your actual horizontal range for angle of fire shots. Another thing I should probably mention here, and I did mention it a little bit before, is that when you're shooting relatively flat angles, like anything under 15 degrees, unless you're shooting extreme range at very small targets, that's not really something that's going to throw you off very much at all. It really takes a pretty steep angle to start throwing you real far off as far as your atmospheric differences when we're talking the difference between your true range and your actual horizontal range for those atmospheric corrections. Your gravitational effects will be significantly different, especially the farther out you go. So if you're shooting over 1,000 meters, you probably just want to account for your actual horizontal range and actually do all your angle of fire corrections just to be safe, because that's getting pretty far. And little differences make a big difference out there. If you're shooting inside 1,000 and it's only a 10-degree slope, a lot of times you can get away with not even really worrying about it. If you watched the video on our 243 shoot, that's an example of it looks like it's a pretty good distance because the actual vertical distance is quite significant. We're on the top of a pretty decent-sized hill, and we're shooting down into a pretty deep valley. But it's at about 1,000 meters or so, or 934 meters or something like that. And it's only like a 10-degree slope, if I remember correctly. I don't remember exactly what the slope was. But the amount of vertical dispersion due to the actual horizontal range change was not a whole lot for that shot. We did correct for it, but actually we had a lot more problems because of our ammunition temperature changing that day. Sometimes when you deploy, and we'll talk about this in internal ballistics coming up very shortly here, but when your ammo changes temperature just sitting out in the sun sometimes, that can really, really speed up your loads. And that's what happened that day. We were missing by just over the top of the head for that 40-inch tall target. So that was actually what was going on. A lot of folks thought that perhaps we were forgetting to adjust for our actual horizontal range, but we actually had accounted for that the difference was an ammunition temperature that day. But we'll get into more detail in our internal ballistics in a minute. But basically what we're communicating here is the concepts of this, and like I said before, when we start building our charts, I'm going to show you some of the best ways to tackle this. And there's different ways to tackle this particular problem. It kind of, your method of tackling this problem is going to hinge on your operational environment. For my current operational environment is pretty flat for the most part where I'm operating. And you're very, very rarely going to have long distance shots with anything over a 20-degree slope. So basically, it's not as crucial for me shooting up here in the flatlands as it was when I was operating in real rugged mountainous terrain. There, you'd actually have to go through a lot more headache and do the full-bore angle of fire correction system. So when we're setting up our ballistic charts, because it does make it a little more complicated if you really want to account for all these differences, particularly the differences in atmospheric drag due to the true range correction that you have to balance with the actual horizontal range part. That can be a little tricky in how you set up your charts. But so if you're operating in mountainous territory, you do want to do it that way. If you're going to pretty much stay in the flatlands, I'll show you the simple way of doing it as well, probably. So don't get nervous if this starts to look a little confusing, especially if you don't have to worry about mountains. But if you are worrying about the mountains, we will get you set up. We'll get you all set up to where you can pretty much get this perfectly adjusted for. One more thing I should cover here as well. If you're using a GPS to do some range confirmations, you have to be aware that most GPS units are looking straight down on the earth when they're calculating distances. So they're going to give you an actual horizontal range reading most of the time. Some of them do calculate your actual elevation. That can be based on barometric pressure differences. And depending on the software of your GPS unit, when it's giving you the distance to your next waypoint, if that's how you're doing your range confirmations, you have to be aware that that's not a true range. That's your actual horizontal range. So that will be okay for figuring out your basic gravitational bullet drop. But when you're talking about your atmospheric corrections, like wind drift, especially wind, you definitely want to get a true range reading. And you'll have to either use your mil dots or a laser or maybe a theodolite or surveying type equipment to figure that out. So just something to be aware of. A GPS is looking straight down. It's most likely going to give you the actual horizontal range rather than your actual true distance. Okay, so before we pull the plug on this video, let's just briefly review the super important points one more time. We have two different ranges. Your true range, which is your actual distance between the firing position and your target, and your actual horizontal range, which is the horizontal distance. And for your bullet drop, you're going to use your actual horizontal range. You're simply going to look up the information for that distance for your drop, and you're going to index that on your optic. All your meteorological corrections and your atmospheric density corrections and stuff like that, and your wind, especially your wind, you can't forget to account for that when you're talking your true range. You want to base that off your true range. If you're basing your wind measurements on your actual horizontal range, that's going to really throw you off, especially at long range or if you're doing a steep shot. And like we said before, the further you go, the more touchy this gets. So the more precise you want to be with all your calculations. If you're shooting pretty close, it's not really going to have that big of an effect. If you're shooting at relatively flat slopes, it's not going to have near as much of an effect. So those are the most important points about this video. That there's the two different ranges, and you're going to have to use both of them to do your calculations. Okay. I think that is basically it for our basic external ballistics portion of the series. Next, we're going to get into some more detail and do some advanced ballistics. We talked before about the different kinds of ballistics. There's internal ballistics, transitional ballistics, external ballistics, and terminal ballistics, right? When we're talking about the subject of internal ballistics, there's all kinds of things going on that can really dramatically change your point of impact. And most of those things are basically uncorrected for by most of the shooting world, because people have a real hard time trying to figure out exactly how to tackle that topic. So we're going to go through that one pretty slowly. We're going to make sure we cover everything in detail. We're going to apply it as we go, and all the different solutions. We're going to talk about various things that either change the axis of the bore as you're making the shot due to internal ballistics changes, or we're going to talk about things that can change the muzzle velocity. Those are the two big categories we're going to cover when we're talking about internal ballistics. So this next video, we're going to dive into things that can basically throw off your shot before it even leaves your barrel, and how to start correcting for those things, or at least deploying your weapon system in such a way that those effects are minimized or kept at a level that is consistent enough to actually adjust for. So the next video is going to be very, very interesting. I think you guys are really going to like this part, so stay tuned. Catch you later.